For our last talk before lunch. And this talk will be given by Dr. Fatkullin from the University of Arizona.
Well, thank you very much for inviting me to this beautiful program and the workshop in particular. It's really a pleasure to be here. So I'm a bit selfish with my talk especially as well. I believe the goal of the workshop is very nice, that mathematicians and physicists kind of interact and learn from each other, especially us mathematicians learn from physicists. So whenever I don't know something, I'm kind of going to ask a question, and you should also feel free to discuss with me right during my talk. I also apologize for changing the title. Since I'm talking 2 workshops, I realized yesterday that I submitted the wrong abstract for the second workshop. so even though I'm going to talk about very similar issues, it's going to be slightly more concentrated on Onsager type models rather than anything else. In particular, I'll actually give a different derivation, so to speak, of Onsager-Meyer-Zoe type model, so which will probably nicely complement what's already been said. Okay, and the questions I want to ask. So there was this, in the last 5 or so years, there was a little bit of activity related to Onsager type models, which somehow, for a long time before that, were semi-invisible for whatever reasons, at least in mathematics community. So now it's maybe stalled a bit again, so it's not quite certain that this much more progress can be done using those techniques and methods. So there's a bunch of questions related to that, and I'll try to formulate mathematical problems a bit later. Okay, let's go further. Something you all know very well. So I'll talk about isotropic nematic states mostly, and phase transition from isotropic state to nematic state. So the Onsager model is one specific model where the main quantity of interest is the probability density of rod orientations. So I call it rho, not f, for whatever reason. So because in mathematics, I guess rho is more commonly used for probability density rather than f. So if it's on a sphere in 3 dimensions, then if we average over the molecules, the probability density is going to be constant, 1 over 4 pi. And for isotropic state, right, like here, or if we have a nematic state, then probability density will try to concentrate at some opposite points on a sphere. Well, we assume here, of course, the molecules are symmetric, which does not have to be general. So it's a particular case relevant to the models I'll describe. Yes, please ask. No, it's very good.
Confused already. What are S and S naught?
S is just a point on a sphere. So rho of S is a density, probability density function on a sphere. So S is a point on a unit sphere. I'll assume it to be
given by 2 angles.
However you like to parameterize it. Yeah.
Okay.
So, and this is just so I'm using this notation to denote atomic mass distribution concentrated at the point at some. Yeah, I understand that, especially when you have a mixture of physicists and mathematicians, it's very hard to give a notation which everybody will accept. So please feel free to ask questions. So this is the typical Onsager type free energy. Even though it's been already called many different names, this kind of energy is here, I somehow like to call it Onsager free energy. And it has the following form. I'll actually derive you a sketchy derivation of this energy from microscopic principles in the next few slides. So it's energy functional. F. It's an energy functional of this probability density of orientation. So it's a functional. And it has 2 terms. It has what we call entropic term and what we call interaction term. In mathematics, again, in physics, actually, you'll see that both of them are in fact entropic in the original Onsager model. But this we usually call entropy, and in mathematics this plus sign, right, rather than minus sign, because we like to minimize things, and this is interaction. So this B2, well, correct me if I'm wrong, so I've heard effective Hamiltonian, but I like to, for example, to call it a second virial coefficient, because it is. So again, I'll derive it a bit later. So this is something which, to many mathematicians who only start working with theory, they think, okay, it's an interaction potential, but it is not. It is certain statistical quantity which appears as a result of averaging, which was already, of course, mentioned here. So the original Onsager's interaction, this effective Hamiltonian, is this absolute value of the sine of the angle. So this denotes the angle between S and S prime. And then Myers-Zaoupé, actually, I still do not know how to pronounce it correctly. If there is a single person who knows for sure how to pronounce Zaoupé.
How's German?
Yeah, okay. No,
So when he lived in the U.S., it was
Not for himself, only for other people.
Okay, so that's the Myers-Zaoupé potential, which we like, of course. The reason, if you look at this function, of course, immediately, why do you like this? Okay, this one has a corner, right? When S is equal to S prime, so it has a corner. And this one doesn't have a corner. It's much more regular. But that's not the only property which actually is useful for this potential. So actually the property which is more useful than the fact that there is no corner is the fact that this is so-called the degenerate kernel. Right? So if you look at this functional, this is, if you try to minimize it, you'll get Euler-Lagrange equation, which is basically known as this Doris-Miałkowski equation. And it's going to be an integral equation where this is the kernel of the integral equation. And this is a degenerate kernel, meaning it's a sum of finite number of functions of S times functions of S prime. So in fact, it's exactly 5 terms, which correspond to the five-dimensional representation of rotation group, because it's due to the fact that this is your Legendre polynomial, second order, which is the sum of spherical harmonics of second order.
Is there any link between this and the crystal growth models where you have sharp cusps in the surface energy plot? Is that the origin for this singularity on Onsager?
I don't know, honestly, but I wouldn't think so. It's probably a random kind of, so I haven't thought.
Any other question?
Yes.
What was the question?
Oh, the question was this fact related to certain singularities in crystalline models, right?
Surface energies.
Yeah, surface energies, which I don't believe there is a connection, but there might be.
No, it comes from how easy is it to intersect two lines. In fact, there should not be a singularity if the rod has a finite radius. It's not actually singular.
So, okay, here is the crash course on the Onsager model. So it's another derivation. So somehow I read this first when I was a student from Doy's book, and I somehow liked that derivation, and I tried to reproduce it from my memory. Hopefully there's not too many problems with this derivation. So how do you derive this Onsager free energy? You do second virial expansion of a free energy. So first of all, you go back to basics of your statistical mechanics, which is, of course, if you start with this, it's already a question, right? So you have a bunch of liquid crystalline molecules, whether they interact with pairwise potentials, which only depend on their locations and orientations of your rod, is already a big issue. So it's not quite trivial, but we have to start from somewhere, right? So let's start with the fact that we have a system of n particles. N is huge. This will be this n. And then the probability density to find our system at locations xi, si, s is orientation, x is location, is given by this generic Gibbs factor. So in its configuration, of course, we already integrated out all the velocities, angular velocities, and all that. And of course, there is no water molecules or anything left like that. So there's many approximations. So then we want to compute the free energy per unit volume, and there's again a big mathematical theory which is partially complete, partially incomplete. The trick is the following: so you compute something which is called the free energy, and then you minimize it, and you claim that whatever you find as a result is the equilibrium state of your system. And in particular, this free energy has the following way. You compute the integral, basically you take the partition integral, right? So this integral is called the partition integral. You just integrate this thing over the entire phase space. But then you don't integrate over the whole phase space. You integrate over certain subset of the phase space, which is given by certain constraints. And in particular, this constraint, for us, since we want this to be a functional of probability density of orientations, we fix it as a constraint. So we look at all the configurations which satisfy given probability density. I mean, there are tricks mathematically, right? So it's actually, if you think how to do it mathematically, you have to do it simultaneously, limit as n goes to infinity, and all those things. It's not, there's work to be done, but it's more or less people have been working on this, and much of it is completed. So you integrate over configurations with given rho, then there's 1 over n factorial is this generic factor in the partition integral. Take logarithm, and you call that free energy. And then you divide by the volume of the total system, multiplied by kT. That's your free energy per unit volume. So you want to compute this quantity. The claim is that, and that's the theorem for some systems, for some others it's speculation, that if you minimize now this as a function of rho, that's going to give you the probability, equilibrium probability density. In reality, of course, what you have is so-called Gibbs states, and this rho will be a certain Gibbs state, which is a kind of measure on infinite system, which is much more complicated than just rho of s. But well, this seems to be working. It seems to work, at least in many ways. Okay, so how do you proceed from there? So you go back here and you multiply and divide this part, this term, by the partition integral of a non-interacting of a free system. So what's the partition integral of a free system? You take the integral over the entire phase space and there's nothing. There's no interaction. You integrate one. So this is simply, if you compute this integral, right, rho is fixed. You compute the integral, you get volume to power n particles, n factorial stays from here. And now what is this? Okay, we have to integrate over orientations. It's a bit tricky thing when we fix the rho of s and want to integrate over orientation. So how you can do it, you can first discretize it, the space of orientations, and then take a limit when discretizations go to, again, so become finer and finer. So you reconstruct the integral. So in that case, you look at this, there will be a product of, so I would be the number of the bin partition of your sphere, and then you look at the number of particles in ith bin. So in essence, now instead of rho of s, you have n i's in various bins, right? So, and how many ways are there to distribute n particles between ni and between I bins, so that in ith bin there is ni particle? That's the number. So a bit of combinatorics. You take logarithm using Stirling's rule, and that's what you recover after a bit of algebra. So now you take limit as n goes to infinity, and you recover your favorite entropy as its rho log rho, because there will be this factor gamma kBt, the energy factor, right? So this n gamma is concentration. I forgot to mention, right? So here, if we go back, so this gamma usually at least proportional to concentration, and so here it shows up because we have n here, right? N, and when we take the free energy per unit volume, we have V here, so that n over V will give us this gamma, the concentration. Now, -1 goes here. There was a minus sign at the end, so logarithm of gamma is here. And then this one, when you increase the number of bins, will give you the integral of rho. So that's how the entropy term appears. So that's, in fact, so observe this, right? The system is thermal, meaning that there is temperature is a just common multiplier, it's a common factor. So of course, in system where there's nothing is interacting, there's nothing really is happening. But you can observe already that you see that this entropy function shows up, and its minimizers are uniform distributions in a sphere. So in other words, if you just look at the Gibbs ensemble of non-interacting rods, so clearly what you're getting is just uniform distribution, which minimizes this functional. And these are constants, which we don't really care about. Now let's go further. So we need to, so as I said, we took this part, we divided and multiplied by that factor, and then logarithm of that factor I've computed. So now there is interacting part where we divided by that thing. So I have a logarithm is taken over from the whole thing. So now this is the tricky part. So this is part where all the approximations are hidden and all the sort of physics mystery, is hiding. So we need to compute now this big integral, right? So this sum, so exponential function of a pairwise interaction, and then we divide again by this common factor. So one way they do it, introduce, if I remember correctly, they call Mayer's functions. So we just take each of these exponentials for pair interaction and represent them for a while as 1 minus Fij. So Fij depends on coordinates and orientations of particles I and j. Then we look at the product. This is going to be a product, right? So we'll look at the product of 1 minus f, which is exactly the exponential, and expand it. So this is basically the virial expansion. Why is it the virial expansion? Because each next term, when we have 1, there will be term with Fij, there will be term with the products, and further on, they all will be proportional to concentration once you take all the integrals to certain power. So like this term will be just 1, this term will be proportional to concentration, next term will be concentration square, and so forth. And that's the virial expansion with respect to concentration. So, and therefore, if you truncate the series, the general belief is that once you truncated the high order terms, whatever's left is still good enough for low concentrations. And that's Onsager model actually is known to work for fairly low concentrations, so that's sort of a justification. In fact, there are certain statements for very specific repulsive interactions which says that if you truncate that you cannot go worse than it's. So if you have transitions for a truncated system, you actually have transitions for the full system. So okay, so you truncate, remove the rest, so you get this kind of integral instead of this, right? And now you look here and you say, okay, I have I less than j, this thing only depends on ij, so you integrate out all the remaining variables, and then you have integrals with over configurations which are given by fixing rho to what it is. So what you left with is actually average with respect to rho of s. Now this is the tricky part because it's not really. So it's not clear that it is. It is, if you think a bit, it looks like yes, it is true, but then you think a bit more, I think maybe it's not. So in reality, the thing which would have been correct, of course, if we had a correlation, so if we had a joint probability density, then it would have been more obvious, and that's. But then the fact that you can go from here to here is not entirely clear. But in some sense, there's a mean field theory hidden, because you'd expect here to be the two-particle distribution function rather than a single-particle distribution function. You're representing it as a product of some sort, which basically is the mean field assumption. And so therefore, okay, again, how do you see that there is a concentration? You see, here is my n times n minus 1. This is just the number of pairs, I less than j. So one of these integrals, if this is translation invariant, will give us the volume, right? So, and now you go back, there is also an extra volume when you divide by v. So you'll get n squared, right, and v squared. So there will be basically a concentration term popping out from this particular. This whole thing will be proportional to concentration. So that's the effective Hamiltonian. You basically take an integral of your Mayer's function over the entire space, and that's what it is. So you compute integral of v of 1 minus exponential function of the pairwise interaction. Now, well, you can look, if you look here and you only consider hardcore potentials, then you can immediately see that that's the excluded volume. That's how the excluded volume interaction comes into this integral equation. Because, see, if the potential is infinity as soon as the particles overlap and 0 otherwise, then this quantity is either going to be 1 or 0. So when this quantity, when the particles overlap, right, if the particles overlap, then this is what? 0, this whole thing is 1, otherwise it's 0. So when you're taking this integral, it's an integral over configurations when the particles overlap. That's the excluded volume. And you also see that this thing does not depend on temperature. And that's sort of, I think, is a bit important observation. So that this B is temperature independent for hard spheres or hard particles, but actually otherwise, if you do this kind of expansion, there will be temperature which will crawl in through this integral, so there will be temperature. And that's how you recover everything, right? Because you've done this integral, so that's what you get, your second virial coefficient or effective Hamiltonian, and you get your Onsager type free energy. So usually, you see the temperature is the general factor in front, so there's no temperature here unless actually you have more complicated interaction. Okay, that's already there. So let me say a few words here. So for the, as been mentioned many times, so that's this derivation is not exactly like Myers-Oab derivation we've seen already. But and also, as it was mentioned, you can actually take multiple expansion of this B2, and if you look at the so quadrupole moment, so there's no dipolar part if the molecules are symmetric, and the quadrupolar part will give you Myers-Oab kernel. So, but of course, in principle, you can try to get Myers-Oab microscopically, just going back to different U. Right, different interaction potential, getting something here which will actually include the temperature. So if you take van der Waals, Lennard-Jones type interaction between the molecules, so there will be something different. So you see, you end up with various theories where the meaning of this gamma and the factor in front of the integral will actually be quite different depending on how you get there. But the general mathematical framework is still the same. So there's no difference mathematically. Okay, let's move. So here's the result, well known for the, at least in mathematical literature, it was obtained by several groups, and everything is trivial except the proof that the axial symmetry, this rho is actually symmetric, after which you sort of obtain all these results, phase diagrams fairly easily. Yeah, so. Even though we still would like to have a nice symmetry-based proof, the consensus between me and Valery is not possible. But because you need to use sort of heavily specific form of this B2 to be able to get axial symmetry. If you, like for Onsager model, like as you said, so there will be actually, if you have Onsager type potential, it's known result in 2 dimensions that in fact if you have 2-dimensional system, there will be higher order phase transition, so there will be minimizers which are not axially symmetric. So there's no reason why in 3D the actually Onsager model will not have critical points. The ground state, the global minimizer will be actually symmetric, but there will be critical points which are not axially symmetric. So it is dependent heavily on the fact that this Myers-Oab form of B2. Okay, so yeah, I'm just reproducing the old diagram.
Do you mean specific model for hard molecule, or it's a general?
No, just generically, if you have this B2, which if you put in this B2, you don't put just the quadruple, like the Myers-Oab part, but you put, say, well, first of all, it's very well known that by now, Jidong, Wang, and Forrest, I think they had a paper where they added just dipolar interaction here, and then the symmetry is immediately broken. So meaning that you will get non-axially symmetric solutions. But well, one can say dipolar, it actually does not respect the reflection symmetry. So maybe that's the reason. But like in your example, you have 6th order, and in fact, this will happen here. I'm pretty sure as well. So if you add the 6th order, you will actually also break the axial symmetry. And it's known example when you go from 3D back to smaller system with 2D, because in 2D you can actually solve Onsager in a way. So in 2 dimensions you can look at the integral equation that you get, and it's going to be, you can reduce it to a Hamiltonian system, single particle Hamiltonian system, and then the profile of the PDF will be just a periodic orbit of that Hamiltonian system. So once you do that, you will realize that if you rotate around equilibrium point once, you will get the axially symmetric solution. But if you rotate, say, 3 times, you will get like little triangle, so it will not be. So there will be things like that. So anyway, so we can talk about this more.
Can you go back to
Yes.
the diagram for a moment?
Yes. So that's the statement that all solutions will look like this. If you fix some polar axis, which will be your symmetry axis, then the rho will not depend on phi, will only on.
And you're using the mathematician's phi and not the
Yeah, I mean,
That's the problem. That's the problem.
actually, I use the physicist one also, but at some point, I was probably giving a talk in the wrong audience, and I changed it because I usually use theta for the.
greatest Travis.
Yeah,
By the way, you also use mathematician's Mayer function because physicist's Mayer function is up to the sign.
Okay, maybe.
Different.
Yeah, signs are always different because it's, we like to minimize things. So,
What's below the line?
so there's two branches. There's isotropic state, always the critical point, and then there is this branch where you have gamma of r given as some function. It's explicit function using some special functions. And along this line, you have this. Right. So if you give yourself a gamma concentration, you look at this gamma. So like you cut it. There will be one prolet state, one isotropic state, one oblate state as the critical points. There will be global minimizer and two saddles, for example, in this case. So this is this kind of diagram. And again, so there's many results available for Myers-O'Leary plus dipolar, two-dimensional, three-dimensional, like extra flow, which is basically like extra shift in the energy. So this, and they all need a little bit of analysis similar to what's happening for basic Myers-O'Leary model. So why do we like that? Well, it's actually very pretty, right? So if you look at this functional, it looks so much prettier than Ginsburg-Landau. No, sure, it's like roller draw. So, and you can recover Ginsburg-Landau fairly easily. So, for example, of course, once you have your rho, you just integrate whatever quantities you want with rho, and you get your order parameter tensor. You get your acute tensor if you want, and then you can actually reduce the energies. So, in our work with Val on two-dimensional systems, we actually gave this little derivation a few years ago, that if you look at this Myers-O'Leary energy in particular, where this is just a second-order spherical harmonic polynomial, like Legendre polynomial, then of course this will give you exactly the Q tensor, more or less absolute value of the Q tensor. So the whole energy, so can be this interaction part is just the Q tensor squared. Now you can introduce a minimizer of Onsager energy given the Q tensor. So because you see, you want to minimize, originally you want to minimize it over all states, but if you minimize it given the Q tensor, it's a constraint minimization problem. There will be a certain minimizer which is optimal for given Q tensor, rho hat. And then you can rewrite the entropy term as the relative entropy. So let me remind you, relative entropy is just the this thing. So relative entropy, and then you have to add this extra term which you subtracted here to get relative entropy. And this thing, now think, if you look back to Myers-O'Leary model, so then this rho itself, this is nothing but the Q tensor again, so it's hidden in there. So once you go here, so this becomes just again a function of a Q tensor. So this whole red thing, is a function of a Q tensor. So in fact, what you have here, you have a function of a Q tensor which can be found explicitly actually, because rho hat can be found explicitly, and the relative entropy. Relative entropy is always positive, and it assumes its minimum when rho is equal to rho hat. So whenever you have a critical point, you will get that this energy is automatically minimized. and this energy will be minimized as well when rho is equal to rho hat. So rho hat will be a critical point. What does this mean? It means that if you look here, and if you look at the entire Onsager model, and you look at the reduced model for just Landau-Lejeune type energy, you get the same critical points in this particular case. Now, so John Ball and Paolo, so they had the work where they suggested just to look at the full Onsager model and do constraint minimization, sort of to minimize first as a constraint with respect to, again, the Q tensor, and then, so it gives the same thing, except, of course, if you do not have the fact that your rho hat, the optimal rho only depends on Q tensor, you don't get this very nice explicit representation like the relative entropy and all that. So in this case, you, like for Myers-Zhou type energy, you have slight bonus on top of that. I don't know if that makes sense, but ask me if I don't make any sense. Okay, so that's sort of another nice thing. So for class of models, you can actually derive Landau-Lejeune type energy from Onsager type energy, and you have a strict result that actually the stability of minimizers will also be the same, and the critical points will be the same, and everything is fine. Now let's go a bit further. So where do we go from these Onsager models? I lifted this very nice image from Oleg's some web page or something. I used to have Wikimedia Commons liquid crystal, but this looks so much nicer. So we want to go a bit further. One of the directions to go from Onsager, of course, go to spatially extended systems. So you want to describe all the patterns. So for this, you need to go to spatial, right, spatially dependent reveal evidence or something like that. So one of the ways is known to like extension of Onsager type theories, density functional theories. This is almost like if you go back to my derivation, this molecular derivation of the Onsager theory, you can do basically the same thing where your rho is x dependent as well. So it is a bit trickier because well, there's more technical issues, but so one of them, sorry, it's mentioned here as well. But it's possible to do, and that's how the density functional theories can be built. Now, there are mathematical questions, in my opinion, and please let me know, especially those of you who know more of physics, of this kind of systems, if this has been done or not. But, for example, one issue is I haven't seen a nice mathematical derivation of actual elasticity from this kind of theory. Well,
there are exact formulas relating elasticity to direct pair correlation functions.
Okay. Yeah, but direct pair correlation function is a mysterious object, right? I don't want
No,
to.
it's just a Mayer function. The lowest order approximation is a Mayer function.
Okay. So yeah, we should talk about it. So because this is, I mean, we should also understand that when mathematicians say derivation and physicists say derivation, there is sometimes a little mismatch. But I would be really eager to see. Yeah. So because one of the issues, for example, was mathematically speaking, there is an interesting question, right? So if you look back to this, so let me go back to all this kind of stuff. There will be terms similar to all these kind of expansions, right? Yeah. Now, if you look, there is no gradients, no nothing like of that sort. There will always be terms only of this sort. Now, how do you get from here to some kind of gradients? Of course, the trick is that if in some weak sense, you see this will vary on a very fine scale, of course, on the scale of maybe molecules. So when you look from far away, in a weak sense, mathematically, this approximates some distribution, which in particular will have basically act as a derivative of certain type. So, and this is what I mean by mathematical derivation. I want to see how a good mathematical limit, when some epsilon goes to 0, will turn this kernel into a derivative. So that's because, like, when many physical derivations, in a way, what they do, they assume the final form and then do some kind of fitting of the parameters. But that will be very, very good to talk about it. So again, so the next question is, okay, can we really get away with this rho of x and s? Even when I talked about the derivation of Onsager model, I really hand-waved through that last part with mean field and so forth. In reality, there will be, for example, if you have a pairwise interaction, you probably want to have at least a pairwise joint distribution function to be able to integrate that pairwise interaction with. So is it true that you can sort of assume that it's a product of independent rows, or is
No.
can you get away with it? So how do you fix it, right? How do you correct it? There are the questions. And again, I don't have a good answer mathematically, and I'm pretty sure physicists have advanced way further than mathematicians. Usually, generally speaking, I think if a mathematician has an answer to a problem to which a physicist doesn't know an answer, the answer is probably wrong, right? Yeah. So, and how far do we need to go? Can we just get away with the second order, say, distribution function and so forth? Okay. So I'm very short on time, so I'll skip some of the results on two-dimensional system, and I'll talk a little bit about this last thing. So this was the slide which was basically sort of a announcement of what I'll try to talk more about during the second workshop. Dynamical phenomenon. Okay, first of all, this free energy formulation that we minimize something and get the equilibrium states is all very nice, but in reality, it's not quite clear that it's works just as well for non-equilibrium systems. And for certain type of non-equilibrium phenomena, it seems to be working very well, but for some others, maybe not. And I don't, for example, know a good benchmark. So when can we do it? When can we not do it? So, but in principle, the whole big program, which is of course impossible to accomplish, that will solve all the problems of statistical physics, right? Is the following: you start with basic Hamiltonian dynamics. And then you want to get to some kind of coarse grain dynamics, for example, which we do on the computer. Nobody really models the actual molecular system. It's impossible. So we always model some kind of coarse grain system already. And especially if we try to use Langevin type stochastic dynamics. There are formalisms how to go from one to another. And so I mentioned a little bit of that. For example, my favorites are so-called Swantik-Mori formalism, when you project onto certain subspace in the space of observable variables. And then you can do Markovian approximation to get some kind of stochastic dynamics, Langevin stochastic dynamics. And this is what you're going to get. You get the coarse grain system when you discarded lots of degrees of freedom, like the solvent molecules, like some internal degrees of freedoms, and you end up, maybe you averaged your director field or autoparameter field over certain mesoscopic scales. So that's what you get, and that's what you generally will be modeling on a computer, right? So then from these dynamics, you want to go to Deutsch-Malachowski type kinetic equations. You can sometimes jump directly, but this jump mathematically is much harder to do than, say, this jump. This jump you can actually do fairly rigorously for some systems. Stochastic systems, there's a thing called propagation of chaos, when you have stochastic differential equations and you can derive kinetic equations. So that's an interesting topic. So I haven't seen it applied to liquid crystalline systems. So if anybody has an ideas about it, I'd be very happy to talk. So finally, after we have kinetic equations, there is an issue of how do these kinetic equations how are they related to the hydrodynamic equations, right? So, for example, equations for the Landau Q-tensor or for the Azin-Frank director field, all these are hydrodynamic equations. The equations for some moments of probability distribution function. How do you get this equation if you have a kinetic equation for the PDF? Well, you try to create some kind of hierarchy of these moments and get equations for them. So, and then you're facing this BBGKY closure issue, because you need high and high order moments, right? And then how do you get it? Sometimes the tricks, there exists some kind of inertial manifold, or There's some decouplings which work, but that's a big unsolved question. So like I remember Pingwing Zheng, so he sent me this summer a similar paper which deals with going from Deuss-Malachowski equation without x, just on a circle, I think, right? Was it circle here? So gets the equation for the moments. So these are the issues, and I think they are okay. So I'll leave that part alone. So I'll be happy to talk with anybody on this, ask you questions if you have any. And so I'll be around for again entire half a year. So I hope we can discuss it. Thank you.
Thanks a lot for your talk, which I think will inspire a lot of questions. So we can't spend much time, but we are pretty on time because we should have been finished exactly 10 minutes past 12. So there is perhaps time for 2 or 3. Please.
So when you say inertial manifolds, do you mean global center manifold? And do you mean a global center manifold for the kinetic equations?
It depends a lot on the type of kinetic equation. So because, I mean, you can have purely dissipative systems, so you can have transport type system equations, right? So it depends. So that's another big issue. Right? So once you get to Langevin type dynamics, it can be purely, say, diffusion in a gradient field, which will correspond to, basically, this will be heat type equations, right? Or it can have transport terms as well, some kind of transport, right, which there will be transport type equations here, and so the type of the well, I shouldn't have necessarily said inertial manifolds, so I should have used a more vague mathematical formulation, sort of attracting sets or something like that, where sort of a smaller dimensional subsets of the phase space where your dynamics actually happens, and where you can show that you get attracted to that particular region. So that would have been probably a better way.
Any more questions?
No. The point about that you raised about elasticity, clearly when you do mean field theory, you neglect or you consider that the pair distribution is the product of the two singles. But this is true only at large distances. So a proper theory, I think, would require proper pair correlation.
Yeah.
And actually, mean field can be dangerous in overestimating phase transitions, particularly in 2 dimensions. So I think actually that the argument of the existence of a true, in the mathematical sense, stable solution in 2 dimensions for short-range interaction, and this is very, very short range, has not been solved yet.
Okay.
You know, because the volume element changes, so you are not going to be stable necessarily against fluctuations if your sample is big enough. So that should be a nice mathematical problem, unless it has been solved already.
Yeah, so that is true. So just as a comment, just a couple months ago when Valeria was visiting me in the US, we modeled a bit of liquid crystals using molecular dynamics for the first time. And it's just amazing how much of statistical physics you recollect and how not similar to your mean field models like Landau-Dejean and similar models, actual molecular dynamics simulations behave. How many phenomena you realize there are, which are not captured by any kind of mean field equations of that sort.
Maybe just a comment that about that second issue about looking at the kernel and the gradient terms. I think Xiao Yu has done numerical work that showed that working with a non-local gradient, you can recover the same behavior that you do from the usual Frank energy, for example. You get the same kind of Frederick's transitions and everything. So I'm not sure that the passage from there is so terribly difficult.
Moreover, it actually may happen that you don't want this passage. So one of the problems, I think, why the Onsager type theories are sort of stuck right now in some ways, because we're trying to substitute them to somehow kind of Landau-Dejean type theories and then go from there. But in reality, why do we even want to go to this kind of gradient of Q type elasticity once maybe having the original ones is even better? easier to work with integral equations without any kind of differential parts. They might be actually simpler to work with.
Because you don't need to start there. You can start with the elasticity based on other arguments.
Exactly.
Well, so then you can just measure the elastic constants and go ahead and calculate.
Well, that is the feasible approach, but sometimes you want to achieve. Some people want to climb a cliff their favorite way, so you want to get to some theory in a certain way to understand how this particular methodology works. And it is possible, of course, to assume elasticity in terms of the expansion.
No, you can derive elasticity from symmetry principles, right? There's a theorem. I think it's a real theorem, right? Goldstone's theorem.
It's a
And then you have the elastic constants. And the elastic constants which you measure are the same as the microscopic constants that are going into the thing on the left. Because you eventually have to measure something, like the critical temperature or something to estimate all those coefficients.
Yeah, so I'm pretty sure. So yeah, I'll be really happy to talk more about this. As I said, it's a question. I'm not claiming to say that it's not answered. I'm just saying that I don't know it.
Yeah, my question is, what's wrong with the standard gradient expansion? Because normally this transition is achieved by the gradient expansion, which seems to be correct in a certain limit. Well, I'm not a mathematician, but I never saw any proof which says there is anything different from the results obtained by gradient expansion of this functional, assuming that there are two different length scales involved in the kernel and in the variation of the distribution function. Then the limit, when the ratio goes to 0, you're perfectly get.
Yeah, I'm pretty sure. So definitely part of mathematics is trying to understand how things work, and part of it is trying to understand how different frameworks sort of interact with each other.
So two comments about that. One way you can deal with whether or not you want to have the gradients is to just say, let me put on a spatially varying field and see what the response of the order parameter is to it. If this field varies slowly, you will find a slowly varying response, and the coefficient of the q² term in that expansion will give you the decay. So if you don't like expanding the grad q, just put on an extra term, which is hij, qij, and your energy, and look at the response of q to h, and you've got...
That's exactly what I call fitting, right? You
No,
put
it's
in
not
some
fitting.
term and then you look
No,
at.
that's not
So
fitting
it's.
at all. That says that you're asking to calculate what is the response that's observable to an external field that couples to it.
Yeah, but
The external field varies slowly.
Tom, you have to prove that if you have a slowly varying perturbation, that it leads to a slowly varying
No, but the calculation will
response.
give that.
You mean a linear calculation? I mean, you do linear response.
No, the calculation, you just follow through there and you'll find a perturbation to the solution he has, which is linear in the external field.
Independent of whatever nonlinearities you have in the elasticity.
Well, within the Onsager theory, certainly.
I think that's what he wants to prove.
The other comment is, I'm not quite sure I see the direction you're going. It seems to me that Onsager is valid for long rods, and it by its nature has all the Q's in it. So, expanding in a particular Q is missing the point of Onsager. It has everything. But whereas the Landau theory is designed for small Q, and it's phenomenological. It's designed to give you the general structure. And even in Landau theory, if you start with a Q2, you will generate a Q4. And then the question is, when are you going to stop? And you stop because at some point, things are small and you don't worry about them. Of course, you have a little bit of trouble because it's a first order transition, and Landau would say, be careful there. But Onsager, I would say...
Yeah, I agree exactly, actually. One should not be trying to combine like Onsager and Landau design types.
So I would say for Onsager, what's more interesting is not to do Q, but to figure out how you get the correct coefficients of n. Because that thing goes into the ordered phase, and there's n appears in every Q.
Except for that when you're seeking for the bifurcation point. If you want to localize the place where the bifurcation takes place, then of course it's kind of a...
But strictly speaking, the bifurcation should have all of the Q's in it.
At the bifurcation, you have only L equal to that matters really. other bifurcation. Of
Yeah,
course,
but-
they do couple.
Yeah,
But you need to know where the bifurcation takes place. Without this knowledge, it's kind of difficult to see what's.
Okay, I have to be rude and to say that maybe it's time to stop now. I hope this discussion will continue indefinitely during the course of this program. But now we have to go to lunch. So we thank all speakers.